Okay, again, we're looking at direction fields for equations of the form y prime equals f of xy, a general first order equation. And as I said, you can do this direction field whether you can solve the equation or not. And it gives you a good idea of the way the solutions behave, even if you can't get an exact solution. And even if you can get an exact solution, it shows you what the solution curves are going to look like. So, well, y prime is the slope of your solution curve at a point xy. So let's do an example of how we do a direction field. Y prime is x squared minus y. Let's just an example. Okay. So what are the slopes of your solution curves in a set of lattice points? Okay. Where a lattice just consists of kind of rectangular grid of points. It doesn't have to be rectangular, but usually it is. Okay, so here we've got x, here we've got y. We can see how the x and y axes are labeled. What's the slope here? Well, it's y prime equals 2 squared minus 2, and that's 2. Okay, so it means that the slope here is 2. It means, well, what's the slope of 2 look like? Well, if I go over 1 and up 2, slope of 2 is about this steep. That doesn't apply over here, but it applies here. So I'm going to try to make a line segment that's that steep. Okay, so do a line segment at the point 2, 2. Having slope 2. Well, we can do the same thing at the other points. If we're at the point 2, 3 halves, then it's going to be 4 minus 3 halves, which is going to be 2.5. So it's going to be a little steeper. Now, I'm not sure I actually made it steeper because these things are already pretty steep. By the time we get down to the point 2, 0, the slope is 4, and that's going to be parallel right here. From this point to this point, we have slope 4, so it's going to be almost vertical. And the slopes in between are going to be a little less vertical. So it's going to be kind of like this. So along this vertical column, the slopes start very steep, but then they get less and less steep as we go up. If we got all the way up to where y equals 4, what would happen? Well, if y equals 4, x is still 2 on this column. 2 squared minus 4 would be 0, and we'd end up with a slope of 0. So as these segments go up higher and higher, if we get up to a point, let's say here, the slopes would actually level off. Now, I'm not going to extend the whole thing up that high, and I didn't make that, I made that a little higher than it should be. Actually, if we got all the way up to here, we'd be a little over 4, and the slope would become negative. Okay, so there's a pattern of these slopes as we go up. Now let's look at a pattern as we go across from y equals 2. Okay, well, if y equals 2 and x equals 0, the slope is going to be what? Negative 2. 0 squared minus 2 is negative 2. So we have a slope of negative 2 here. And if this is slope of 2, slope of negative 2 will be equally steep, but in the negative direction. Now, if x equals 1/2, but 1/2 squared is 1/4. 1/4 minus 2 gives us a slope of a little less than 2, 1 3/4. Not going to look much different than this. It's going to be hard to make that accurate. But here we do this. And I actually made that one steeper, so that's a bad idea. So I'm going to make it a little less steep, but there it is. Now, by the time we get out here, of course, the slope has become positive. But if x equals 1, the slope is still negative 1. Okay, 1 squared minus 1 is negative 1. So that's going to be somewhat less steep. By the time we get out to 3/2, the slope has all of a sudden become positive. Y is 2, x is 3/2. 3/2 squared is 2 1/4. So we have a very small positive slope here. So we have a pretty drastic change between here and here. And the change occurs when the squaring of x starts to take over the value of y, okay? Because x squared starts increasing much more quickly and very quickly overcomes the y equals 2. Okay, now if y equals 1, the slope here is going to be negative 1. And at 1/2, it's going to be negative 3/4, a little less steep. At x equals 1, the slope is going to become 0. At x equals 3/2, the slope is going to be 1 1/4. Okay, so we see how the slopes go as we march across here. Then we can look at how the slopes go as we go vertically here. If y is 1/2, then the slope is negative 1/2. If y is 3/2, then the slope is 3/2. Okay, steeper than this, but not as steep as this. So we see the progression of slopes. The slope when x is 0 is just going to be negative y. So the bigger y gets, the steeper the thing gets, and it's always going to be in the negative direction. Now, if we went down below the x-axis, you would repeat these slopes as you move away from the x-axis, but they'd all be positive. Okay, so we could talk about how the slopes go here. And of course, at the origin, the slope is 0, then you're going to have kind of the reflection of these slopes. Okay, well, we're not going to map this whole thing out everywhere. So we just want to look at how this works and then look at what it tells us. Look at the picture it gives us. Okay. If x equals 1/2, x squared is 1/4. So the slope is going to be pretty close to the slope here, but not quite as steep. Comparing the slope here to the slope here, it's a little less steep because your x squared gives you 1/4. By the time x equals 1, well, now the slope is leveled off here. For y equals 1/2 and x equals 1, you're going to get 1 minus 1/2, which is 1/2. So you're going to have a fairly modest slope here, and then your slope up here without going into a lot of explanation will be like this. The slopes here were x equals 3/2, x squared is 2 1/4. So your slope here is going to be 2. Slope here is going to be a little less than that. Slope here is going to be a little less than that. And there you have what's called a direction field. Now, what good does this do? Well, if you have an initial condition, so an initial condition which would be that when x equals some number, x naught, then y equals some number, y naught. And this just gives you a point in the plane. So let's just say your point in the plane is right here. Then by the existence theorems, if this is a continuous function and differentiable, that doesn't even have to be differentiable. If this is a continuous function, you're guaranteed a solution, which means you're guaranteed a solution curve within whatever part of the plane this function is defined, okay? You can see that for at this point, our slope is going to be somewhere between this slope and this slope. So it's probably going to be something like this. Now, as we continue on, we're going to go down in this direction. And by the time we get down here, the slope's going to be like this. So the curve has to be curving around a little bit to agree with what we see here. And then it's going to have to come over here and start curving up and then start curving up more and more rapidly. In other words, it follows the trend of the direction field. So this is what our solution is going to look like. And it's going to pretty much look like that no matter where we start. So we could draw the whole set of solution curves through various points. Okay, we expect if we start here, thing gets less steep. Thing gets steeper as we move up. If we start at this point, then we're going to probably be a little steeper than this, but it's going to come down and encounter this. It's going to do this. If we start over here, then it's pretty clear that we're going to come down like so, come around here and come up. Wherever we start, our direction field directs us along these curves. So I could do more, but we get the whole family of curves and we see how these solutions tend to behave. Now, this is a first order linear equation. We're going to learn how to solve it. We don't yet know how to get the solutions, but now we know that whatever our solutions are, they're going to be functions of x and y. And those functions are going to give us a curve. Y is going to be some function of x, okay? If we set f of xy equal to some number, well, we can go on from there. Gives us a picture of our solutions. Okay, hopefully that makes some sort of sense. And it should also make sense that no matter what our function f of xy is, we can create a direction field. Of course, there's software that'll create the direction field for you, but we don't want to use that at this point. Later on, when you're trying to analyze something pretty complicated, where it would take you hours to even figure out what to look at for the direction field, then going to the software might be a valid thing, but you want to do this by hand so you get some idea of where the software might mislead you, restrictions on the validity, and so forth. So I don't want to be too specific about that right now until you get your hands on it. Okay, now a couple of things. If I continue looking at this function, I think I misspoke a minute ago. I'll clarify that. Okay, I said your function f of xy is your solution, and I referred to it as though that's your solution. It's not. Your solution curves consist of whatever the solutions are. Y is going to be some function of x. That's going to give you a curve. Now, f of xy also gives you curves, and here they are. So f of xy equals c. These are important for understanding and constructing direction fields. Rather than just setting out a grid and seeing what you get, you look at the structure of your function f of xy and see how it dictates what your curves are going to be as you move around the plane. And it's fairly easy to do that for a simple function like this. For a very complicated function, well, that's what software is for. Okay, so for this curve, f of xy equals c tells you that x squared minus y is c, so that well, I'll go ahead and say minus c. In general, c is a constant, and you don't even have to use a minus on it, but since I'm being specific here, then we're going to use some values of c. We want to see how this behaves. So when I give you a value of c, then your curve is going to be y equals x squared minus c. Okay. What's this tell you? First of all, y equals x squared minus c is just a very simple parabola. It's your y equals x squared function, vertically shifted c units. C is positive. It's going to be vertically shifted down because of the negative c. If c is negative, it's going to be vertically shifted up. Okay. And that's going to explain a lot of what we see over here. So on the parabola y equals x squared minus c, all slopes in our direction field are c. Because f of xy equals c, and the equation is y prime equals f of xy. In this case, specifically, f of xy is x squared minus y, so solutions here. Well, the direction field here has this characteristic. What's that tell us? Well, I'm going to sketch this in all quadrants. First of all, we have our y equals x squared parabola. Okay. And this is y equals x squared minus 0. That implies our slopes are 0 because our slopes are c. This means that we can just put a bunch of horizontal line segments through this curve. Now, this curve doesn't have any significance for our solution. Well, actually kind of does, but doesn't have any great significance for our solution. But it has a lot of significance for the direction field. Because look here, where are our slopes 0? There's 0 here, here, somewhere up about here. Okay, so if I sketch the y equals x squared parabola, slope is 0 here, slope is 0 here. It's somewhere between here and here, the slope will become 0. And somewhere between here and here, the slope will become 0. Because again, slope is negative here, a little bit positive here. I probably don't have that located exactly right. I don't have my slopes exactly right, but there it is. Okay. So we can see this y equals x squared curve with slope 0 everywhere on the curve. makes sense in terms of the direction field that we just sketched. Well, now our C equals 1 curve, where the slope should be 1, and where are our slopes equal to 1? Well, slope is equal to 1 about here. Something's not going to be quite right. Yeah, it is. It is. I'm not looking at it right. Okay. Slope 1 will occur about here. Slope 1 will occur about here. Something's bothering me about that, but let's see what happens. Okay. Okay, then y equals x squared minus 1. Hopefully this will work out. Let's just say minus 1 is here and 1 is here. Okay. So the graph of y equals x squared minus 1 is going to look like this. Something like this. Pretty crude. Then a slope of 1 occurs at every point with this. Okay, so this is slopes are 1. So I draw slope 1 here. Slope 1 here, getting a little steep there. Slope of 1 here. Slope of 1 here. This curve is making me want to make some of these things too steep. That one's still too steep. So actually slope 1 will be almost parallel to the curve. Didn't do a good job with slope 1 there. Going to be easier to do on this side, I hope. So slope 1 would be like this, like this, like this, like this. Okay, that's where our slope is 1. Now, where are the slopes 1? Well, I didn't do these 3 grid points, but at every one of these points, y is 0. So slope will be x squared, which will be like 1/4 here. Small slope. Slope of 1 is going to occur here when x equals 1. A slope of about 2 1/4 occurs when x equals 3/2. Okay, again, not drawn that well, but where do we find slopes of 1? Well, we had a slope of 1 down here. We have a slope of 1 here. And a slope of 1 will occur somewhere between here and here. Maybe it'll be about here. And if we sketch a curve showing where slopes are 1, actually slope of 1 is going to occur to the left. That slope is 1 1/4. We would have a curve like this, the slopes of 1 along this curve. Okay, that makes sense in terms of what we see. Now, along y equals x squared plus 1, the slope will be -1. So if 1 is here, then x squared plus 1 will go through here. So it's going to look like this curve. And the slopes are going to be -1, which will be about like so. if we follow these slopes, like we did over here, we see that if we start here, we're going to have to come down like so, and then curve around, and then start going up again. Okay? And if we follow the trend along this curve, we see that these things are going to continue on. And I haven't drawn enough to get that. But what if we start here? Okay, our slope is positive, becomes 0, then it becomes negative. Okay, but then it comes down here and starts going up again. So we see these curves as part of a curve that behaves like this. Now they're going to keep getting steeper here, so they're going to keep going up. They're going to keep getting steeper over here, but in the positive direction, so they're going to curve back down. But this is in general what your curves are going to look like. Now there are more subtleties to the way these curves behave, but we see that the use of isoclines allows us to get the same information, but it allows us to more intelligently locate our slopes, because we can do equal slopes all along the isocline. Isocline means, iso means same, cline means like incline, same incline, okay? Isocline. Okay, that's a big deal. Okay, now your text now goes into quite a bit of discussion of autonomous equations. Excuse me. An autonomous equation has a characteristic that y prime is only a function of y. Okay, well, this means, let me just draw in general the way it works. This means that for any value of y, we draw a bunch of lines for y is constant. And that implies the slopes are going to be constant. Now I hope you can read that. Just says lines are y is constant. Y constant implies a slope, which is f of y, is constant, because y is constant. F of y is going to be the same everywhere on each of these lines. So it becomes pretty easy to sketch your direction field. Now let's just say your direction field looks like this. Now say I just do the same slope all the way across here. Okay, and let's say that the slope is, well, I'm going to do slope 0 along a couple of these lines. Okay, let's just see what our solution curve looks like if you have this field. Now remember, only for autonomous equations do you have the same slope all the way across on each line. But if the equation is autonomous, f of y is 0 on this line, f of y equals 0 on this line, and f of y is less than 0 between these two lines. So you have negative slope between these two lines. Now, if the slope is 0 here and 0 here, and f of y is continuous, then assuming there's no place between here and here where the slope is again 0, we can see what our curves look like. Now, the way I've sketched these curves, it doesn't look like there should be any place between here and here where the slope levels off. Slope is negative, then it's negative but steeper, but then it's negative but less steep, and now it's leveling off again. If I want to construct a solution curve, let's just say I want to start here and construct a solution curve. Okay, well, I'm going to have to go down pretty steep here, but then I'm going to get less steep here, and I'm going to approach 0 steepness, so it's pretty clear that the curve ought to look like this and become asymptotic to this line. And since it's still going down, it's going to continue still going down, assuming that we have an accurate depiction of the direction field. Now, if I want to go in this direction from this point, well, my slope is going to have to become less and less and less. And I'm going to get an asymptote here. You get this kind of sigmoid shape. Okay, it's one thing to observe. Another thing, well, let's just say I start here. Okay, well, let's see. The slope has to be pretty small here, but increasing. So it's going to come down like this. It's going to come down like this. And it's going to come around here. It'll look like this. And then here it's just got to become asymptotic. Okay, now if I've done this accurately, we're going to be encountering the same slopes starting from this point that we would if we started from this point here where the y coordinate is the same, so that this curve should be just the same as this curve, but moved over, just a horizontal shift. And the curve should be identical. And this curve should have been a little steeper here. This one looks steeper here than this one does, but just because I didn't draw it very well, looking at it from this angle, that's my excuse. If you draw it accurately, these curves will be convincingly identical in shape. Okay, so identical shapes horizontally shifted. Now, what happens on this side of where f of y equals 0? Well, we don't know. We don't know what happens beyond this, but now our solutions are clearly going to at least start out like this. Okay. And they're going to continue until we reach another curve where y is 0, or c is 0, but f of c is 0, f of y is 0, okay? where f of y is constant, okay, and 0. So we might have sigmoids that look like this. Well, between lines where the slope is 0, remember f of y is continuous, so its value of f of y between two lines, consecutive lines where the value is 0, where f of y is 0, the function is either going to have to be always positive or always negative, because you can't go from 0 to positive to 0 with a continuous function. You can't go from a 0 to a positive value to 0 to a consecutive 0. There's a word I'm not getting. You can't go from one 0 to the next 0 of the function. If you change sign, because if you change sign, slope has to be 0 at the point where the sign changes. It's your basic idea of pre-calculus. So you got to maybe understand that. Okay, so anyhow, you can have this kind of behavior. Okay. Between consecutive zeros, the function's either got to have positive slope everywhere or negative slope everywhere. Again, because you can't go from positive to negative with a continuous f of y without going through 0. Okay. Now, of course, there are 3 other solution curves we can draw here. I'm only going to draw one of them. I'm going to say that this line is a solution curve. And so is this one. I guess I will draw them. Each of these lines where f of c is 0, or where f of y equals c equals 0, is a solution curve in itself. So that if you start anywhere on this line, y prime is always going to be 0, meaning y is never going to change. So that's your solution curve. This is your solution curve. This is your solution curve on this line, and this line. Now I'm running out of space. I almost wish I left myself more room here. See what else I can say. I can say on lines where x equals constant, you have a horizontal solution curve. You call those values of y equilibrium values. So we call those equilibrium solutions. Okay, equilibrium solution here, equilibrium solution here, equilibrium solution here. And what I'm getting at now is if you move a little bit on one side of an equilibrium solution, you're either going to be moving away from the equilibrium solution curve or toward the equilibrium solution curve. Okay. Right now, if x increases, then the solution curves move away from the equilibrium, both sides. On this equilibrium curve, on this curve, as x increases, the solution is approaching equilibrium. Okay, now we don't know what's going on the other side of this, but if it's also approaching from the other side, you're going to call this a stable equilibrium. Okay. Everything approaches that equilibrium. Okay, you call this an unstable equilibrium. Things try to go away from the equilibrium. An example from physics. This is an unstable equilibrium. Just the random fluctuations in the net force on this by the atmosphere, even if I have it balanced perfectly, are going to quickly knock it off and it's going to fall. Okay. Yes, I hope I kept my reflexes in control there. You didn't hear a sonic boom, did you? Okay. I was lucky to catch it without breaking it. Fairly long and fragile. And I used more force than I should have. But I managed to keep it from penetrating my palm. So, okay, well, okay. That's unstable equilibrium, okay? This is stable equilibrium. If I move the thing a little ways from equilibrium, it comes back. Well, you can take that by analogy to this behavior. Along here, if I get moved off of my equilibrium curve a little bit, I go away from equilibrium. It's like the thing falls, okay? If this curve on this side of this line, as well as on this side of the line, approaches the equilibrium, then moving off of the line will tend to will result in a tendency to restore equilibrium. Okay, kind of like a pendulum. That would be a hanging pendulum is a stable equilibrium. You move a pendulum a little ways from equilibrium, it restores. Okay, a nail balancing on its point is unstable as heck. And that's the way the phase space shows us that it's going to work. Okay, well, I think I've exhausted what I can do on this board. I can probably use this one. I've got plenty of board space to use. Okay. So what I want to do is I want to kind of repeat. Let's see how much of this I can still see. Yeah, I can't see enough. So let me just kind of construct another. You should understand the picture I'm drawing. I'm not going to do a lot of labeling. If my phase space looks like this, then my solutions up here, at least on this side, are going to approach like this. My solutions between here and here are going to look like this. My solutions between here and here are going to look like this. And my solutions between here and here, don't know what's going to happen down below this. We've got to stop somewhere. And this will be sufficient to the example, are going to look like this. Okay, so I could draw a couple of these here, and I could draw a couple of these here, a couple of these here, and another one of these here. Okay, so this is kind of my flow in phase space. This equilibrium is unstable because you tend to move away from equilibrium. This equilibrium is stable because everything tends to move toward the equilibrium. This equilibrium is weird, okay? And I don't have a good example of that. I haven't even tried to think of an example, but it's a mixed, okay? If you displace the system on this side, it tends to restore. You displace it on this side, it tends to move away from equilibrium and doesn't come back, okay? And you could work that out in physics. You could have some kind of weird force field that doesn't overcome a pendulum on this side, but it's stronger on this side, so it pulls the pendulum away if it gets away from equilibrium. Okay, and you can sketch a vector field that you think might do that. And it actually would be a good exercise since you've had the physics and the multivariable calculus, understand vector fields. Wouldn't be a bad thing to think about, but I'm not going to, at this point, require it. I'll probably put it in the finals, but don't worry about that. Probably won't do that. Who knows what I'll do at that time. Okay, so we have unstable equilibrium here. Stable equilibrium here. And your book uses a different term. And words aren't coming to me that easily right now, so I'm just going to say mixed equilibrium. You'll see a different term for that in your book. I don't want to try to remember what that is. I kind of know, but it's not coming to me. Okay, so that's important behavior. Now, a phase diagram. Let's see what your function f of xy, what this tells you about your function f of xy. Okay, first of all, we're going to do a phase diagram. And you have your equilibrium. Okay. You have an equilibrium at this value of y, an equilibrium for this value of y, an equilibrium for this value of y. Okay. Above this value of y, at least for a while, the slope brings the curve toward the equilibrium. Below this point, the slope brings the thing toward equilibrium. So here f of y is negative. Here f of y is greater than 0. And of course, here f of y equals 0. Now between here and here, f of y is again negative. Here f of y equals 0. Here f of y equals 0. And here f of y is again less than 0. Now remember that for this to work, I've got to have all the y values for f of y equals 0. I can't leave any out. If I leave any of them out, there could be another equilibrium in between. There would be another one in between some of the zeros. And the picture wouldn't work, okay? And remember that f of y between consecutive zeros can't change sign because the only way a continuous function can change a sign is to go through 0. Very important idea that hopefully gets reinforced in pre-calculus, which is where really all this starts. But our pre-calculus courses are so watered down that I don't think that idea really takes hold. And of course, I had the experience of not even having had a pre-calculus when they threw me in to big old theoretical calculus at a very school with very high standards. Didn't offer anything below calculus. So I had to figure out pre-calculus. I missed a lot of stuff. There's a lot of stuff that came along in my curriculum that I had to figure out because I didn't know it. So I know what it's like, and I know how you can stumble over things. Makes things a little harder. You don't learn quite as much. Of course, eventually I learned everything there is to learn, but you know, I don't like to talk about that. I'm too modest. Okay. Well, I learned some stuff. There's a lot of stuff I didn't learn, and would have learned better if I'd had a better foundation. Now, to make up for that, I had a great foundation when I went to college with logic, and my algebra was totally solid. So, yeah, I'm not complaining about my background. And having to figure out pre-calculus was actually kind of good for me in the long run. Still, I see how when you miss pre-calculus or miss things in pre-calculus, it handicaps you later. Especially if you're not as stubborn as I was and refusing to admit defeat and figuring it out for myself. Okay. If I was smarter, there might have been some really good stuff. Okay. You live with what you got. Okay. End of digression. There's what we see about F. And you see where you really have to have a good command of pre-calculus to understand this well, without having to do too much thinking about it, making it easier to learn your differential equations. Okay, now let's go back to what this tells us about the graph of f of x, or f of y. So if we have y here, and f of y here, what's the graph look like? Well, I haven't put a scale on this, but let's say that y equals 0 here. Now, depending on your function, there's probably other important points you could mark here, and you can see examples of that in your text. But just assuming y is 0 here, then I know that f of y is 0 here at some point slightly to the right of 0. So that means that the graph of f of y versus y has to go through this y-axis, okay? That might be weird having the horizontal axis be y, but there's nothing sacred about y here, x here. It could be p here and q here, s here and u here. Could be anything. Right now it's f of y vertical, y horizontal. Okay. Then there are two other points where f of y is 0. And f of y is 0, of course, where this graph goes through this y-axis. So let's see. This 0 occurs a little further to the, you know what? Something ought to be bothering you. If I regard this direction as the positive y direction, and this direction is a positive y direction, then this 0 is on the left-hand side of the vertical axis. Now let's go on. Then here you have positive values of y, where f of y is 0. This one is further on the positive side than this one is on the negative side, so it's going to be on the positive side a little further from the origin than this one. And then this one is that much further on this side. And again, f of y is 0. So the function goes through every one of these points and only through these points. Now, on this side of the 0 here, which would be the positive side, f of y is negative. So if I want to draw my f of y curve, let's find a likely color here. Okay, so f of y is going to go from negative to positive at this point. So the curve has to kind of go through like this. It won't be as straight as I drew it, but we get the idea. Okay, this point, it's positive on this side, negative on this side, so it's going to come back down through here. Then, between here and here, it's negative. So, to the right of this 0, the function is negative. But on the other side, it's negative as well. So here, it's got to be negative coming from this side and negative on this side. So that means the function just doesn't actually pass through the y-axis. It touches the y-axis here. So now we can draw a reasonable facsimile of our function. Okay, we think the function does this. Now, we go to the right here. We don't know if it's just going to go on down toward negative infinity or if it's going to turn around again. We haven't included that information. We haven't taken our phase diagram or our direction field that far. And probably not a good idea to draw on this part, because this thing could turn around again very quickly, or maybe it never turns around. Or maybe it turns around, but only gradually 12 feet that way. I don't know. Depends on your function. Well, now you see why it's important to be able to graph a function of a single variable efficiently without having to plug in a bunch of points or use, heaven forbid, a graphing calculator, which gives you no intuition. Although if you can't get any intuition, you can maybe look at what the graphing calculator says and then figure out why the curve looks that way. That's not a bad exercise. You don't reach for the calculator immediately. You don't reach for technology immediately. And you use the kind of graphing skills you learned starting in pre-calculus and then in calculus to construct the curve. And then from the curve, you can construct this phase diagram. That's what this is called here. Okay, here's your direction field. You have an autonomous equation, y prime equals f of y. And here's a graph of your function. So you could start with a graph of the function, figure out your phase diagram, construct your direction field. And of course, another thing, you got to be able to find the zeros of this function. Okay. In the graph, and you got to be able to find out where the function is 0. And sometimes it can be really hard to determine where a given function is 0. Sometimes you have no analytic solution. You have to do an approximate solution, and then you got to worry about all the calculus. Does Newton's method work here? Or is this one of the cases where Newton's method blows up? You know, what do you do? Okay, lots of stuff you got to worry about. But there it is. There's a picture of a pretty good picture, I think, of what you can do with autonomous equations. I'm going to pause the video for a second. For direction field that looks like this, We don't know what happens up here. We don't know what happens down here, but it depends what happens to this function. If this function just takes off to negative infinity, then you're going to have solutions that approach negative infinity. They might or might not approach it in something that maybe looks exponential, or maybe even, it could wiggle a bit before it comes down to your asymptote here, okay? That's kind of a maybe. That could happen depending on the function. The function would have to change slope in here without the function would have to fluctuate here in order to make this sort of thing happen. But it couldn't go through zero again. Okay, well, just alerting you to the fact that lots of things can happen. You kind of got to work them out. Okay. Finished a little bit early. I've got about 5 minutes. I'm going to give you a little introduction to separable equations. And the idea is very simple. Let's say that y prime equals x squared y. Okay. Now we can write this as, well, first of all, let's go ahead and put it in Leibniz notation. dy dx equals x squared y. Now, as you know, and you've seen in other courses, you can't really do algebra with these dy's and dx's, but we act as if we could. And you really want to understand why this works, but it works. So we can write dy over y equals x squared dx. And then we can integrate both sides, giving us a natural log of the absolute value of y equals x cubed over 3. And we really need that integration constant plus a constant. So that I'm going to put it this way, y equals ae to the x cubed over 3. Now, that might be within the watermark. Y equals ae to the x cubed over 3 plus a constant. Now, that's all very simple. Okay, I assume you understand that because you've seen separable equations before. We just didn't call them that. Now, if this function over here is such that it's a product of an x function and a y function, then you can always do this. And if it isn't, you can't. Okay, so this is a product. That's a dx there. I didn't have room at the edge of the board to really write it well, but you get the idea. Okay, you got to read about this in your book. And these equations are very simple to solve. You got to apply initial conditions and stuff. In this case, it's a times e to the c, e to the x cubed over 3. Since c is a constant, okay, be this for any old day. Except I don't think a can be 0. I don't think that hard right now. phase zero, then you end up with a division by zero problem. Actually, I think A can be zero. I don't want to do that. Okay. But anyhow, there's your solution. And then you have a one parameter family. And you can find A according to single condition on the solution. And that condition might be on the derivative of the solution. So I'm not going to call it an initial condition, but often it'll be an initial condition. Something about a point X naught, Y naught on the solution curve. Okay, so just a quick blurb on separable equation. That's all there is to understand, but your book goes on a little bit more about it, so I'll do the same thing. Okay.